Good morning. So, this is the tutorial session for the third week. In this week we have looked at the Navier-Stokes equation, the derivation of the Navier-Stokes equation, and the definition of fluid rotation, vorticity vector, stream function, potential functions, Euler and Bernoullis equation. So, some of the concepts we will demonstrate through some tutorial problem. So, first we take up the application of momentum equation. So, this basically it is a fluid. So, we have a fluid here and there is a plate on top of the fluid. The plate is moved at a velocity u1. So, we want to the statement of the problem is find the velocity profile given that v velocity is 0 everywhere. So, this is a two dimensional flow, steady flow, not changing with time, and incompressible flow. So, let us see if we can start from the general form of the Navier-Stokes equation and get to a solution of this velocity profile. So, first thing is the mass conservation equation or the continuity equation. So, for the 2D steady incompressible flow, it is the form del u by del x plus del v by del y is equal to 0. So, this is in this case also we will see that this is very important to utilize the mass conservation equation. So, as the v is identically 0 everywhere. So, v velocity is 0 everywhere. So, it means that del v by del y is also 0. See, one thing we have to keep in mind that velocity 0 does not necessarily means the gradient is 0, but in this particular case because the velocity is 0 everywhere, that means identically, then the gradient has to be 0. So, we can drop out the del v by del y term, but del y by del x is del u by del x is non-zero. So, directly, but because del v by del y is 0, so del u by del x is also 0. So, what does that mean? It does not mean that u is constant, because this is a partial differential equation, u is a function of both x and y. So, del u, if you take a derivative of u with respect to x, it can be 0 if u is a function of y. So, in general we can write from here u as a function of y, because suppose u is y square, if you do a partial derivative of y square with respect to x, it will become 0. So, in general we can write u as a function of y. So, in physically what it means is that it means that u is not changing along x direction. So, if you take say at some point in x here, let us say x1 and x2, the u velocity, and that means the velocity profile itself, because this is applicable throughout the flow. So, the velocity profile does not change along the x direction. This flow, this kind of flow has a different name also. This is called fully developed flow. When the flow in a particular direction does not change along that particular direction everywhere, it does not change along that direction, then it is called fully developed. It has developed completely. Anyway, we will come to that again while discussing pi. So, that means velocity is non-constant, but its variation is only along y and not along x. Now, let us see x momentum equation. So, while dealing with this kind of a problem, what we can do, at least the way which is demonstrated here, we start with the full form of the x momentum equation and see what terms can be neglected. So, we start with the full Navier-Stokes equation, okay, x momentum equation. Then we see what terms are negligible here. So, first of all, this is a steady case. So, this term goes out. So, this is 0. Then see, we already got del u by del x is equal to 0 from here, right. So, if we use that criteria, then this second term also vanishes, it goes out. Then see, v is 0. So, this term also goes out. See, to begin with we do not do anything, we just to deal with this kind of a mathematical problem, we start with the full form and see how the terms drop out. So, the third term also drops out. Then what happens? Then we have del 2 u del x 2 as 0, because of course, if del u by del x is 0 everywhere, not at a particular point, everywhere this is 0. So, that means if you take a second derivative of that, that will also be 0. But again, just to remind us, if del u by del x is 0 at a particular point, it does not mean that del 2 u del x 2 is 0, but it is identically 0 here. So, this drops out. So, we see here that this term also del 2 u by del x 2 drops out, it is also 0, because del u by del x is 0. So, identically 0, that means 0 everywhere. So, del 2 u by del x 2 will also be 0. Now, this reduces to this form, that means now you can write, you are left out with only two terms on the right hand side, del p by del x or minus del p by del x more specifically, plus mu del 2 u del y 2. Before going further with this equation, let us look at the y momentum equation. So, the y momentum equation looks like this here, as shown here. Even the y momentum, even though the v velocity is 0, in this case it is important to consider this equation, we will see why. So, because v is 0, see all the terms actually disappears here are 0, del v by unsteady flow or v is equal to 0, both will tell you that the first term is 0, the second term is also 0 because v is 0 everywhere, del v by del x is 0, this is also 0, this is also 0 because v is 0 everywhere. So, all the terms are 0. So, that means what are you left out with? You are left out with a very important conclusion that del p by del y is equal to 0, that means p is a function of x. So, as you see here in this particular problem, u is a function of y, that is the velocity changes in the y direction and the pressure is only changing in the x direction. Okay. So, the u velocity is fully developed, it does not change along the x direction. The p, the pressure is actually only changing in the x direction. So, this information is important to reduce this equation now, because if p is purely a function of x and u is purely a function of y, then this can be now written as in terms of not partial derivatives, but total derivatives. So, we can write this as d minus dp by dx plus mu d2y dy2 is equal to 0. So, this equation now let us see, we can, if we can solve this equation essentially means that mu d2 u dy2 on the left hand side is equal to dp by dx, and this should be equal to a constant. How can we say confidently that this can be this will be a constant? Because see, on the left hand side we have purely function of y or its derivative, second derivative of something which is purely a function of y. On the right hand side we have p which is purely a function of x. A function of y and x, they can be only equal if both of them are actually constant. So, we can easily write this as constant. Now, by doing this, after doing this, it is easy because this is a constant, we can easily integrate this equation. So, of course, this comes from the fact that u is only a function of y and p is function of x, that we already said that we can write it as constant because of these two factors. Now, we apply the boundary conditions. The boundary conditions are that at y is equal to 0, the no slip condition is valid, u is 0, and at y is equal to y, again no slip condition is valid. That means this is equal to u1, that means the velocity of the fluid touching the lower surface of the plate has the same velocity as the plate. So, that is also no slip condition. So, in both ends here we apply the no slip conditions, that means there is no slip between the fluid and the plate with which, or the solid object with which it is in contact with. So, by applying that condition, and we can easily integrate this equation, it will come in this form. If you just do this integration, so this is basically double derivative of a function is constant, which this constant in this particular case is given as dp by dx. So, if we do that particular integration, we get with this boundary condition, we get this as a analytical solution to this problem. So, analytical solution means u is known as a function of y directly. So, in this two form. Now, what we can do is, so you can apply the boundary condition and see that it automatically satisfied. For example, if you put y is equal to y1 here, this term becomes 0, and y is equal to y1 here, this becomes u1. So, u becomes u1, and if you put y is equal to 0, so if you put y is equal to 0, then what happens? Then this term becomes 0 because of this y, and this right hand term also becomes 0. So, this also satisfies this boundary condition. So, this is a quick check for anything, so that to make sure that we have applied the boundary conditions appropriately. So, now if we go forward with this solution and try to actually see how the velocity profile is. This gives us some interesting insight into the problem. So, for example, we start with the first case where dp by dx is 0, that means this drops out, that means there is no pressure gradient, only the plate is pulling the fluid, the plate is only with the help of shear, it is actually making the fluid flow, there is no pressure gradient. So, then you have a very linear profile like this. So, this is basically the solution. On the other hand, if you have del p by del x, let us say, is greater than 0, what it means? That means if you go along x direction, pressure is increasing. So, dp by dx is greater than 0 means that, because if x, as x increases, pressure is also increasing. So, if the pressure is increasing along the direction of the flow, then it will actually try to oppose the flow. So, that kind of a pressure gradient is called an adverse pressure gradient. So, dp by dx greater than 0 is an adverse pressure gradient, and we get a velocity profile like this. So, this velocity profile actually means that here on the x axis we have plotted u by u1, and the y axis, on the vertical axis we have plotted y by y1. So, as you can see here, it meets the boundary conditions at y by y1 is equal to 0, u is 0, u by u1 is 0, and at y by y1 is equal to 1, u by u1 is equal to 1 in all the 3 flows, all the 3 cases of dp by dx. So, you are talking about the adverse pressure gradient. So, what it does is basically it tries to oppose the flow, and you get a velocity profile like this. We will see in the next chapter that basically this adverse pressure gradient is something which is responsible for flow separation. So, we will see that later, and there is a third situation which is called a favorable pressure gradient, that is dp by dx is less than 0. So, it is less than 0, that means it is negative, that means if you go along this direction, then the pressure is reducing. So, flow will have naturally a tendency to flow in that direction, the fluid will have a natural tendency to flow in the direction where in which the static pressure reduces. So, this helps the flow, that is why it is called a favorable pressure gradient, and we will see that this favorable pressure gradient will never cause a flow to separate, that means detach from the surface. So, we will discuss that, this will be useful while we deal with the boundary layer flow in the next chapter. But overall this problem demonstrate how systematically we can apply a particular flow situation to the general form of the continuity and the momentum equations. This is the first case. The second case in the tutorial is this particular problem. This one demonstrate the application of Bernoullis equation. So, let us see what is the statement of the problem. So, find the velocity at the probe pitot tube location from the mercury manometer reading. So, let us explain the problem here. So, let us say this is a flow again between 2 parallel plates or through a channel. We want to find out velocity. So, this is actually a probe to measure the velocity. How it measures the velocity? What we can do is if we put a particular tube here which is called a pitot tube. So, if we put this tube here, so the flow will stagnate in front of it, and then if you have a manometer, a mercury manometer, let us say in this particular case, it will, this stagnation pressure will actually push the mercury head down, and then the other side, if it is connected to the flow itself, this will go up, and by noticing this reading, this h reading, we can find out the magnitude of the velocity at this location. So, how does this velocity relate to this h? So, let us see that if we can derive it using the Bernoullis equation. So, for that we know that the Bernoullis equation is applicable along a streamline. We consider the stagnation streamline. What is the stagnation streamline? So, let us look at this part of the flow carefully. So, this is the tube now. So, this is your tube, the pitot tube, the tip of the pitot tube. The flow is coming along the streamline and stagnating here. So, this dot shown at the tip of the pitot tube is the stagnation point. If you remember our derivation of Bernoullis equation, what it said is the sum of the dynamic pressure head and the static pressure head, that is constant. Now, what happens is the velocity here, the particular velocity here in front, little front of the pitot tube is u, but as it comes here it becomes at the tip of the tube the velocity is 0. It has to be 0 because the flow cannot enter the pitot tube. If it enters the pitot tube, this mercury will come out of here. So, this does not have enough pressure actually to enter into the pitot tube. It just produces a stagnant layer or a stagnant medium inside the entire tube, but the flow, what it does, it because it stagnates at the tip, so it increases the pressure within this layer, within this fluid inside the tube. As a result of this high pressure will push the mercury level down. So, this is the stagnation pressure line, the stagnation stream line. We can apply Bernoullis equation directly here. So, as we can see, the static pressure at A, so if we take this as a point A, rho u square by 2 plus static pressure is equal to the stagnation pressure here, because the sum of this 2 has resulted in this stagnation condition. So, if we go forward now, if you see this stagnation pressure here is almost equal to P c. We say it is almost equal to P c because there is a level difference between the C and the height A. We have neglected the weight of the fluid in this particular tube. That is okay because this height is generally very small, or this density is also low if it is just an air flow. So, they are more or less same. Now, P c can be also written as P b plus this particular head. So, if you look at the pressure here, what is it supporting? It is supporting this, if you draw a straight line along this is supporting the pressure at P b plus the liquid height here, which is very small and the density is also less. So, this pressure P b and the essentially this P b and the mercury head, the difference in the mercury head between the two limbs of the manometer, that is H. So, rho Hg is the density of the mercury and rho Hg, Gh is basically the Pc. So, now this means that P stagnation is basically Pb plus this. So, we can plug in the P stagnation value of this into this equation here. If we do that, what we get is basically an expression for velocity. So, the velocity which we are trying to measure using this pitot tube is equal to square root of 2 multiplied by P stagnation minus Pa by rho. Now, what is the P stagnation? P stagnation we saw here, that P stagnation is this. So, if we plug in P stagnation as Pb plus this into this equation, what we get? We get this expression. We get this as Pb plus this minus Pa is equal to rho. Now, we cannot proceed because further, because see, this is Pb looks like from here is unknown. What is Pb? Let us understand what is Pb. So, basically this Pb is the wall static pressure, the static pressure at the wall, which is measured by, which is sensed by this limb of the manometer, this left hand side limb of the manometer. Pb is basically the wall static pressure. What we have here is Pb and what we have here is Pa. So, how does this Pb and Pa relate to each other? So, this is a very important thing. Unless we resolve this, we cannot get the velocity. Let us see how we can get that. So, for getting that, we can take the help of the last tutorial which demonstrated the application of the Navier-Stokes equation. If we remember, the y momentum equation was something was this, and for this we said that all the terms actually vanishes. What are we left out with? We are left out with del p by del y is equal to 0. So, this is a very important thing. So, you see the pressure variation along y direction is not there. So, if pressure variation is not there in y direction, that means the wall static pressure and the static pressure at the center of this channel, that is Pa, both are same. So, Pa is equal to Pb. Once you do that, once you use that information, that Pb is equal to Pa, you get an expression for velocity. So, velocity is basically, so what you measure in this condition is basically the height of the mercury in the manometer. You know the density of mercury, acceleration due to gravity, and rho is the density of the fluid which is flowing through this channel. All these are known to you, you can get the velocity. So, this demonstrate two things, one is the application of the Bernoullis equation, and secondly a probe which can be used to measure velocity in a flow. This is called a pitot tube. Then we go to the third problem. The third problem relates to the streamline, the application of the concepts of stream function. So, the question which is asked here is, find the condition for which a conic section will represent a streamline for an irrotational flow. So, I think you are familiar with this term conic section. If you are not, just to give some indication, a conic section is actually represented by this equation. So, this is basically a general equation. If you look at it, it has ax square plus bxy plus cy square plus dx plus ey plus f is equal to 0. So, this is actually an equation of a curve. How do you get that curve? You take a cone and you take the section of the cone. If you take it is, if it is a plane parallel to the base of the cone, then it will form a circle. If you take a plane at an angle with the base of the cone, then the intersection of the cone and the plane will not form a circle, it will form an ellipse, or it will form a parabola or a hyperbola. So, so when it forms a ellipse or a circle, a ellipse or a parabola or a hyperbola depends on how this particular coefficient relates to each other. There is something called discriminant. So, this discriminant is defined as b square minus 4a into c, it does not depend on this. So, it depends on this particular coefficient. If that is equal to 0, it is a parabola. If it is greater than 0, it is a hyperbola, less than 0, it is an ellipse, like that. So, we will see. So, this is just from basic our high school mathematics. So, we see, if we suppose we have a streamline which has this equation, and we are also saying that this is, the flow is irrotational. So, what is the condition that this equation can represent a streamline of an irrotational flow? So, this is basically the question. So, the streamline represented by a conic section will be given as, okay. So, suppose now this was just the conic section, equation of a conic section. The streamline represented by this curve will be given like this, because psi x comma y is actually a constant along a streamline. For a particular streamline, psi x comma y is constant, and the function is given by this equation. So, this f can be taken on the other side, and we can get this particular equation of the streamline. Now, the second thing is, we have to apply irrotationality condition to this. What is the irrotationality condition? So, this is a two dimensional flow. Irrotationality condition only says that omega z is equal to 0, that means del v by del x minus del u by del y is equal to 0. Okay. So, if we apply this condition now, it means that del x of minus del psi by del x and minus of del y of del psi by del y. So, that means psi function or the stream function satisfying the Laplace equation. This we discussed while introducing stream function also, that if a flow is irrotational, then the stream function, of course it is 2D, because the stream function we are defining for a 2D only. So, the stream function, if it is a irrotational flow, the stream function will automatically satisfy the Laplace equation. So, if we apply that particular criteria to this function, what do we get? We get something very interesting. We introduce this function into this equation, what we get is, of course this is the Laplace equation. So, what we get is something like this, that means this is the first term, del 2 del x 2 of psi, this one is the first term, we have plugged in term by term, we are doing the derivative, and this is the second term. So, if you, so this implies, this equation implies that this should be equal to 0, although this looks like a big equation, but actually what we have done is we have plugged in this value into this. Once we do this, what we get see this one xy bxy, you take a double derivative with respect to x, the first time it will be by and the second time it will be 0, it will disappear. Same here, because this is just a function of y, same for this, because this is just x to the power 1, this is also this will also disappear. Del y2 of x2 will also disappear, this one will also disappear, because this is y to the power 1 and we are taking a double derivative, and this term again, this is a function of x and we are taking double derivative with respect to y, it will disappear, this also disappears. So, finally, we are left out with this two terms, what it gives us is 2a plus 2c is equal to 0. So, for if this is the condition which it has to satisfy. Now, let us see what when will this condition be satisfied. So, that means a is equal to minus c, simple, and then if we find the discriminant of this conic section, this is v square minus 4ac, right. So, if we plug in this expression, which is always true if the flow is an irrotational flow. So, if we plug in that criteria here, what do we get? We get this as b square minus 4a into minus a, which is b square plus 4a square, and this is always positive, because b square is also positive, a square, of course, these are not imaginary quantities. So, this is always the discriminant is always positive. So, this will always represent an hyperbola. So, a conic section will always be a hyperbola if it represents a streamline for an irrotational flow. So, this is the third problem and the last problem in this tutorial section. This brings us to the end of the part C, or the third chapter or the third week of the first module of this course on fluid dynamics and turbo machines. In this chapter, we have looked at the differential analysis of fluid flow. We have started with the derivation of the general form of the Navier-Stokes equation. Of course, we have taken a two dimensional, we have gradually gone into more into a two dimensional and incompressible flow. Then we looked at different important concepts like fluid rotation, vorticity, stream function, potential function, Euler equation, Bernoullis equation, and the applications of this equation to some specific situation, like measurement of fluid velocity, application to a particular situation of the fluid flow, and also some problems on stream and potential function. So, this brings us to the end of the third week of this course. The next week we will take up the flow, three different types of flows: the flow over a flat plate, the flow over an object like a cylinder, and also the I think pipe flow. So, the pipe flow. So, these three types of flows we will deal with, and where we will see again those are practical cases where this integral and differential analysis will find very good applications. This last two chapters, the second and third chapter, were more about analyzing mathematical procedures for analyzing fluid flows. In the next chapter again we will see some practical situations where this analysis will find application. Thank you.